always some finite positive number. And so that means that if you want to know what the sign of the change in entropy, that's not hard. That's just the sign of Q in. Well, did we add heat or take heat out during this expansion up here, this constant pressure expansion? We added heat. Did entropy then go up or down? Entropy, which way, up or down? Yeah, because if Q in is positive, delta S is positive. Okay? All right, I didn't calculate it because it's a nasty integral. But when the dust clears, when we're done, we better get a positive number out, right? So you might still wind up being asked to calculate what the entropy change is from this point to this point of the problem, but it might be the way you'd solve it is that you've already solved another part, but you figure out what the entropy change was along some other route that took you from there to there. Turns out entropy is a state variable. So if you know what the entropy change is when you go from there to there along some other path or something, well, it's going to be the same this way. Just the same thing for energy. Suppose you knew what the energy change was when you went from here, down to here, over here, and make a little circle, and you go up to there, and you wind up there. Well, as long as you started there and ended there, and you know what delta E is, that's the same for any other path you take. So you might be through a problem, and you've already calculated the change in energy, right? Through some other path, and then you got a new path. Well, it won't work to say, oh, the work's the same. Well, that may not be. The energy, the Q might not be the same. The heat exchange might be the same. But the change in entropy will be the same. The change in energy will be the same. The change in V, the change in N, well, N doesn't change, N constant. So it's zero no matter what path you take on this graph. Anyway, that's the idea. So, okay, super. We looked at a bunch of other examples. Let's consider the example that where T is constant, because that's a case that's easy to calculate. No need for an integral. Actually, there's two cases that are easy to calculate. But let's do the one where T is constant. All right, we divide these out. So this right here, all this stuff was for constant pressure, right? Now let's do it for constant temperature. What does that look like? Well, we worked it out last time, and we talked about it right here. If you start off at this point right here, and then you move to the right on the PV diagram, right? This is an expansion. We go left to right. It goes like this, right? It curves along. So that's a constant temperature expansion. V goes up, P goes down proportionally, right? Because PV must be fixed. Why? Because temperature, right? PV equals NKT. That means T equals PV over NK. So if you double V, you better have P. Does that make sense? To make the temperature the same. So that means that change in the temperature equals 0. That means change in the energy of the gas equals 0. What about the entropy? Did the entropy of the gas change? Well, to figure that out, let's use that formula right there. What is the heat exchange? What is the heat added to? Well, first of all, was heat added or removed in order to achieve this path? How do we figure that out? Well, we know the energy didn't change. How about work? Was work done by the gas? Work done on the gas, or work is equal to 0? Which of those is it? Yeah, it's an expansion. Whenever you've got an expansion, gas does positive work on the outside world. In other words, work on the gas is negative for any expanding gas. Right? The fact that arrow's pointing to the right, I don't care what squiggly line this is. I know that tells the fact that arrow's pointing more to the right than the left tells me that it's an expansion. That means the gas did positive work on me. So work by the gas is positive, work on the gas is negative. That means that if the energy didn't change, right, by the first law of thermodynamics, right, that means the only change in energy, the only thing that changes the energy is well, no, I'm thinking the wrong way. No, the energy didn't change. It says that whatever change there was in energy due to work had better be equal and opposite to change to heat exchange. In other words, Q in equals negative work on, right? You have to cancel each other out, so the change in energy is 0. And what does that equal? Well, we worked out last time. Remember, it came out there was a log in it because we had an integral of 1 over integral of x of 1 over dx over x, right? This is a log. So we got nkt times the log of the ratio of the volumes, and it's the bigger, well, for an expansion, it's the second volume over the first volume if there's a minus sign for work on. However, there's a minus sign here. I'm going fast and loose now, so I just cancel my minus signs out. There's a minus work on. You had a minus sign last time for work on, that got canceled because of that. So let's see if this makes sense. You guys told me correctly that in order to go from here to here, the gas did work. So work on the gas was negative. That means Q in had better be positive. I got a positive sign here, positive, positive, positive. Log of a bigger thing over a smaller thing, right? V2 is over here, V1 over here. Great, I got it right because that corresponds to a positive change in the entropy when I went from point 1 to point 2. Did I get that right? Does everyone agree with that? Yeah, good. A lot of opportunities for errors here. If I was thinking through what I try to. It's tough when people are watching or on an exam, but keep your wits about you. Just check everything, make sure it makes sense. So good, we saw an increase in heat was added, right? That means that entropy go up or down during this process for the gas. Entropy of the gas went up. We added heat to the system, and it did useful work for us, right? Its work on the gas was negative, meaning the gas pushed out on that piston. We could have hooked it up to part of our car, right? We could have used that to move our car to do some useful work. So right, delta S then, not only can we say that it's positive, we can calculate exactly in this case using a simple formula. For constant temperature, delta X, the change in entropy is just equal to the heat added divided by the temperature of the system, which in this case didn't change, very simple. So it's just Q in over temperature. Well, look at this. Q in actually is proportional to temperature in this case, so the T's just cancel out. So what you're left with is N times K times the log of V2 over V1. So let's think about that. That's a simple enough formula, right? There's one is Boltzmann constant. Okay, big deal. That just converts our units essentially from energy to entropy type units, right? Because this is just a number of particles, right? That's a unitless quantity, if you like. This is a unitless thing. So what's going on here? This is telling us that the change in the entropy is just given by some geometrical factor, right? What happened? We doubled the size of the chamber that's holding the gas particles, and the entropy went up. In fact, it went up by the log of the ratio of the volume. Well, actually, times N. You remember? So N times log of something is equal to log of that something to this guy's power. Is that right? Remember that? There. What did I just say? I said log of A to the B power is equal to B times log of A. And that's a fun fact from your past. So what does that do for us here? It says that I can rewrite this. Here, let's rewrite it. And say, well, that means this is equal to K times the log of the ratio of the volumes, V1 over V2, all taken to the power N. And all this is inside the logarithm. Just so it's clear, this isn't the logarithm to that power. This is inside the argument of the logarithm. Okay? What is this? What does that mean? Well, suppose we double the volume. Okay, so V2 is 2 times V1. Okay, well, that means this whole thing equals K times log of 2 to the nth power. Well, I'm not going to myself a lot of space here. Oh, sorry, it's so messy. To the nth. I'm just trying to illustrate, more entropy notions with my messy writing. So K times log of 2 to the nth power. So 2 to the nth power, what is that? Well, oh, look what I did. Here, let's look back at my expression. So I wrote that this expression is almost true, but the units are wrong. Entropy doesn't have no units. It's got units of Boltzmann constant. Got to have a K in front. So units should have told me right away that even though this had the right limiting behavior, if I look at these things, oh yeah, it's working. The units are wrong. So a lot of physicists leave K out. They say, oh, we're just going to equate energy and entropy. We just set K to 1. In this class, we don't do that. So I should be disciplined and make sure I don't skip stuff like that. So what do I mean by accessible states? If you have a bunch of particles in a box, and they can be on the left side of the box or the right side of the box, each particle then has, well, if you double the volume, if you go from this volume, V1, right, to this volume, which is twice as big, say, right, twice as big as V2, which is 2 times v1. Well, you just did an expansion. You've increased the number of places you might find each particle inside the box, right? Because right here, suppose you break it up into little cubes and say, okay, here's every little place you might find the particle. Now, this is a problem back in the 19th century. People realized there's this conundrum. They said, well, when you talk about entropy, the number of accessible states is infinite. I actually had an AP student or AA student come out here sometimes and said, look, what you're saying can't be true. There's an infinite number of places you can find the particle. So that means the entropy is always infinity. So that's a great observation. In fact, because of quantum mechanics, it turns out that there's a sort of a smallest size you can localize the particle. And for this class, that's all you need to know. We'll talk more about opposite hours. But the bottom line is that there really is just a finite number of places where you might find a particle in a box, if you like. So think about it at the level of this class. So you say, all right, if that's true, then if I double the box size, I double the number of little cubby holes I might find the particle in. I double the number of accessible states. You might say, well, wait a minute, but you told me that the entropy here is log of the number of accessible states, and we didn't find that it went up by factor 2. It went up by a factor of 2 to the nth power. Ah, that's because if you have n particles in the box, how many states can the system take? Well, here I got an example, right? I've got this is a box with some gas particles in it, and they have to be very nicely arranged right now. Sort of, it doesn't happen that way very often, right? They're all in one, so like this is oxygen, that's nitrogen. All the oxygens on one side, nitrogen. That's it for equal mixtures. Okay, so maybe it's not nitrogen. Maybe these are places that are vacant. So this is a place where there's a gas molecule, if you like. So all the gas on one side of the room. Don't breathe that when you're canning. I would never do that. But that's what this sort of corresponds with, right? So that for one thing, that never happens. It never happens that all the oxygens on one side of the room, right? Even briefly. Even though it's a logical possibility, nothing's controlling where the gas molecules are in the room. But well, anyway, I'm getting ahead of myself a little bit. Let's just finish this idea. The idea here is that if I only allow the particles to be on one side of the box, like the box is this big, and then later I expand it, I do an isothermal expansion, so the box doubles in size, right? And let's say there's a little cubby hole here. All these are little cubby holes, and how many are there? 1, 2, you can count them, right? It just doubles the number. Well, if you want to know for 2 particles how many states can the system take on, well, it's the number. Like the first particle can go in any one of these spots when I double the box size, right? And then the second particle can go in any one of the spots. You say, well, they can't be in the same box. Maybe. Okay, fine, but if n's a big number, n minus 1 is equal to n. It doesn't really matter. So it turns out that it goes like 2 squared, or let's see how I say it. Oh, I see. The ratio goes like 2 squared. Oh my goodness. So let's do this. Let's define little n to be the number of places you can find the particle inside the smaller box v1, and then say how many states of the system are there. So number of states of system for n particles in v1, right? What is that? Well, the number of states. They write this as omega, but anyway, I think I'll just write this. Number of states. The number of states for v1, right? And n. Well, I can put there's n places I can find there's little n places I can find the first particle, and then there's n minus 1, okay, this is approximate, almost the same thing as n places I can find the second part. Right? And there's n minus 2 places, that's the same thing as n. So, and so on. So what is this thing equal to? Well, it's pretty much equal to little n to the nth power. Well, for v2, how many number of states are there? States of system, right? How many configurations are there if I've got n particles and I have v2, which equals 2 times v1? Well, that means that now n goes to 2n, right? Like n up here becomes 2n. So here we'll say 2n cubby holes, 2n places per particle. So that means that the number of states of the system equals 2n times 2n minus 1 times 2n. Anyway, you get the idea, right? And you wind up with 2n to the nth power. If you take the ratio of, so what's the ratio of the number of, so if I say what's delta s, right? That's equal to s final minus, or whatever, s for the size v2 minus s for the system at v1. That's the same thing as k times ln of the ratio, right? Because the difference of the logs is the log of the ratio, right? So I've got number of states of the system for v2 over number of states. Bear with me, I'm almost done with this. If this is helping you making sense, it's great. If it's not, don't sweat too much. But I want you to get an idea that these things are related, these two formulas for entropy. The bottom line is that if you take the ratio of little n to the nth power over little 2 times n, right, to the nth power, you get k, you get log, you get, what is it, 2n to the nth power over little n to the nth power. Well, the n's to the nth power, little n's to the nth power cancel out. So all you're left with is 2 to the n. K times log of 2 to the n. So after all, once again, the shouting stops and the just layers and everything else, well, you get the same expression we already found another way, right? This expression we found by using the formula saying, oh yeah, delta S, that's just equal to, for a constant temperature process, it's just Qn over temperature. That's all it is. Add some heat to the system, you increase the entropy. Right here we said, well, let's think about accessible states. The number of accessible states, by how much did that change? The ratio of the number of accessible states is 2 to the n. That's a big number, right? N's Avogadro's number, 2 to Avogadro's number. That's huge, right? Again, it's a huge difference. So it's really not a trivial thing to double the size of a box and let the gas expand. You better get some useful work out in that process. If you don't, you lost something, and you're not going to get it back. Like, entropy universe went up, and you get it again. So great, so the entropy increased. So when you do an isothermal expansion, the entropy of the system increases, just like it did over here when we did a constant pressure expansion. But wait a minute, I told you before that anything you can draw in a PV diagram really can be thought of and is a reversible process. Entropy went up. Is this not reversible? Well, entropy went up, but it's only the entropy of the gas in the cylinder in question inside the box. It turns out that the energy you had to add, the Qn you added, had to come from somewhere. It had to come from some other thermodynamic system. Usually a heat bath, we call it. Kind of funny name for it, but we have this thing that provides heat. It itself might be an ideal gas. In fact, if we put it in contact, we put the two in contact. Remember like the demo I did a couple lectures ago, last lecture, where I expanded gas in the cylinder, and I did it slowly, and I let the gas warm up as I went by taking heat from the outside world. So I expanded it. Well, the air in the room was the heat bath providing the heat to the gas inside the cylinder as I expanded it. I moved the plunger back. And in particular, the thing that's important there is that the temperature of the air in the room is the same as the temperature of the air inside the gas cylinder. The result is that if I calculate the change in the entropy for the gas, we just did that for an isothermal process, we find it goes up. But what about the entropy of the gas in the air in the room, right? The air in the room, the entropy there actually went down because it lost heat. It's really important, right? So if I want to know what's the change in the entropy of the universe as a result of my expanding isothermally the gas in the cylinder by pulling back slowly on the plunger and letting the pressure inside the cylinder go down, right, as the volume goes up, and I do it slowly so that heat is exchanged from the outside world inside, and everything's always at the same temperature. The inside and outside, they're always at 300 Kelvin. They're always at room temperature the whole time. In that case, all the delta S's we calculated here were of the gas in the cylinder. We can also calculate delta S of air in room, right, or if you like, of the heat bath, and that is negative the same amount, right? It's the same calculation we already did, right? Because what is Qn going to be? Well, it's going to, let's see, what's the formula? It is, for constant temperature, it's just Q in for air, I'll just say room okay, to indicate this is air in the room, over T of the room. Well, T of the room is the same as T of the gas. I'll just call it T. And Qin is equal to negative Qin for gas and cylinder. Gas and cylinder. Does that make sense? So as far as the room air is concerned, Qin is a negative number. It gave up heat. It went into the cylinder, right? So then what you wind up with is exactly the same expression we had before, but with a minus sign in front. It's negative K times, what is it, log of 2 to the n, where, you know, n is still just a number of, and so what do I mean by this? The n I must mean that is the number of gas molecules inside the cylinder, right? Not in the room. But it's the same n as I used before. Number of molecules in cylinder. In the system I was describing earlier. Cylinder. Anyway, yes. Okay. So what I just walked you through was, if heat is exchanged from one place to another, and both places are at the same temperature as each other, right? They're at the same temperature. And in fact, in this case, it's even easier than that. They don't even change temperature during the whole process. So the temperature T is the same throughout the whole process. It's easy to calculate the change in the entropy. It's equal and opposite for the two things exchanging the heat, right? And the result is that the universe's entropy change, so D change the universe, you might say, wait a minute, there's other things happening in the universe. Well, that's true, but let's say what the change in the universe is due to this process alone. What do I mean by that? I mean that I sum up delta S for the room air, right, plus delta S for the gas in the cylinder, right? And it equals 0 in this case. I could have gotten a positive number if I did something that was irreversible. It'd be positive, right? This thing that's reversible, I get 0. And it is reversible. I can go back and forth. I can now compress the gas very slowly. And if I do that, heat will be exchanged. Heat will come out of the cylinder or into the room air. And if I do it slowly enough, right, so that everything's always at thermal equilibrium the whole time, the temperature never changes, and really slowly, I'll get back to where I started. I've reversed the process. That's what I mean by reversible. I can get back to where I started, and I can do so without having to add any extra work. You say, wait a minute, you have to do work to compress the gas. That's true. But the gas did work on me when I expanded. So if I stored that up by compressing a spring and having potential energy in the spring, or if I stored it up by lifting a weight against gravity or something, potential energy to gravity, that potential energy could then be used to compress the gas again, right? So that's what I mean by reversible. Entropy changes do happen locally during most reversible processes. But the universe does not change its entropy. If you think it's irreversible, entropy goes up. Entropy never goes down. And I can say never pretty strongly. I guess we could get into philosophical or detailed discussion about fluctuations, and then you can have some. It just turns out though that it's a really good rule of thumb. Entropy never goes down when you add up all the parts of the system. For a closed system, in other words, entropy never goes down. So it's different than the laws we have for energy. For energy, energy is conserved. If you account for all energy in the system, it doesn't go up, doesn't go down. It's always the same. Entropy is not that way. Entropy can go up for a closed system. We've only looked so far at reversible processes. Even the case, remember the case where I compressed the cylinder really fast, and a little paper inside burst into flames because the temperature in that gas went really high, really fast. Went above the flash point of the paper, went above 51 Fahrenheit, right, and burned the paper. So in that case, there was, so first of all, for a process like that, where I compress the gas really fast, and let's say there's really good insulation around it, how much heat exchange is there? What's Qin in that process? Fast compression, super fast. Yeah, 0. It's trouble with the outpouring insulation. I went so fast, there was no time for the temperature to equilibrate the gas world. I should say, there's no time for heat to be exchanged. Well, then Qin equals 0, right? So let's think about the entropy change in that case. So now what we're doing is this. We're going from here. Oh, okay, let's do a compression. So we'll go from here and we'll go whoop like that, right? It's a compression because I'm going to the left. PV diagram as always, right? I go to the left, it's compression, and it's not isothermal. Here's what I would have gotten for an isothermal process, right? So in fact, the pressure went higher for the change in volume, right? If I did an isothermal process, if I shut the volume by that much, that's what I would have gotten, right? So here's a case where there's no heat exchange. The temperature go up or down. That's bigger than 0. That's right. Let me remind myself what things I want to say about this. There's a few things I want to say about it. One is, so yeah, we already said, what distinguishes this process is that Qn equals 0. This is one of those crazy adiabatic compression. Again, a bad word because adiabatic and other things, but it just means a fast compression, so heat can't be exchanged. It just means that Q equals 0. That's all I mean by this. Q equals 0. The work's not equal to 0, though. Was work on positive or negative? Yeah, I did work on the gas to compress it. So I know it's bigger than, and we worked it out last time. I'm not going to go through that math all again, but actually it's not too bad. It's easy to calculate. What do you think? The easy way to calculate that, because by the first law of thermodynamics, the only way you change the energy is by adding heat. There was no heat exchange. So then all we have to do is just, as long as we know what P initial, P final, V initial, V final are. So if we call this V initial, V final, this is P initial, P final, right? If we know what those things are, it's actually not so bad, right? Because we know what the change in the energy has to be, right? This is just going to be the change in the energy minus Qn. Oh yeah, but that's 0, right? What is the change in energy? Well, if we know the P's and the V's, it's P final, let's see. It's 3 halves P initial, P final, V final minus P initial, V initial. You agree? I think that's right. So in other words, the work on it is positive, right? Because the energy went up, and we know that because this product is bigger than that product. Because P is bigger than it would have been had it stayed on the isothermal. Good. So I think the signs are correct. I think the formula is right. This doesn't fully solve our problem. Maybe if you weren't given these things for an isothermal compression, you might be. It depends on how your problem's set up, right? The book works out for you. I think we did it a little bit last time. But it doesn't even matter. The point I want to make now is what is the change in entropy? So what is the change in the entropy of the gas during this process? Yeah, 0. Kind of weird, huh? So I compress the gas. And what's the formula going to be? Well, the temperature isn't constant, so I need the integral. Oh, right. What is the integral? It's dq